Hello, I'm Vinay Balamourougan, and with me are Eunsan Mo and Jessica Graham. For ORS, we chose to research the inverse design of electronics using machine learning.
In this project, we applied machine learning to the inverse design of circuits. In general, the engineer will have to adjust certain parameters, such as the voltages and currents, then see how these values would affect their bandwidth, gain, and etc. Rather than going through the process of trial and error to find these desired values, we tested out 3 different machine learning algorithms to see which one was most suitable to solve the problem of inverse design. We trained them to take in 6 resistor values and use them to predict the gain. Linear regression was successful to some degree and provided the most accurate results. Neural networks and the polynomial regression were not as accurate, but worked with around 100 data points. We concluded that the second-degree polynomial may have been overfitted to the training set.
Designing of a circuit by hand is very cumbersome. It takes a lot of time and money. Just imagine calculating values of hundreds of resistors, capacitors, and inductors by hand. It gives me a headache just by thinking about it. With this in our mind, we want to automate the process of designing a circuit as much as possible. We will approach this problem using an inverse design. What does that mean? We will write a machine learning algorithm such as neural network, linear regression, polynomial regression that takes in a desired output of a circuit as an input and pumps out n parameters for the given circuit.
The 3 algorithms we tested out are linear regression, polynomial regression, and neural networks. Neural networks have been shown in studies to solve the inverse design problem well because they can handle the nonlinear relationships. For example, in one study, a neural network was used in an inverse design problem to predict what geometry and shape was needed in order to achieve a certain response from a sub-wavelength structure. They were also shown in another study to help design microwave filters by helping them to achieve geometrical parameters from electrical parameters. Linear regression was also used in a microwave circuit. In this study, they found that linear regression performed the inverse space mapping of a microwave filter faster than the neural networks did. Polynomial regression does not seem to be used in inverse design so far.
For our experiment, our goal was to accurately model the behavior of the amplifier circuit using different machine learning algorithms. The circuit has 6 resistors that contribute to the gain of the amplifier. We chose these elements to be the parameters that we adjusted in our experiment. The 3 machine learning algorithms that we used were linear regression, polynomial regression, and neural networks. We chose to use multiple algorithms to see which would produce the best results. Eunsan and Jessica worked on the linear regression and polynomial regression algorithms while I worked on the neural network. For each algorithm, we first wrote the forward paths to better familiarize ourselves with the process of modeling a circuit. This is a more traditionally seen process that takes inputs to obtain outputs. In the context of our experiment, this involves training our algorithms to predict the gain based on resistor values. Afterwards, we move towards the inverse design, which essentially takes in the outputs of what we're modeling and returns inputs. This was how we attempted to reach our final goal of being able to predict resistor values based on a single gain. Some of the tools we used to carry out our research are Python, MATLAB, ANSYS Electronics Desktop, and HSpice. Python was used for wrapper code and neural networks, while MATLAB was used for linear regression and polynomial regression. The wrapper code was essentially the loop we used to generate samples and automate the process of running simulations with different parameter values. We chose to use different languages because there are certain toolboxes that we found to be helpful for our respective algorithms. For example, When writing the code for the neural network, I used NumPys, Pandas, and Keras to assist me. ANSYS and HSpice were circuit simulation softwares that we used. I chose to use ANSYS for the generation of training and testing examples because there's a relatively simple method to adjust parameters, run simulations, and obtain data using Python. My partner Eunsan used HSpice, which offered its own advantages. Once familiar with writing netlists, HSpice can be much more straightforward. The graphs on this slide show our final results for each algorithm. Linear regression is shown in blue, polynomial regression in orange, and neural networks in green. Each algorithm returned a prediction of resistances. Comparing these predicted resistances to our target resistances is not a clear representation of the accuracy of our algorithms because there are different combinations of resistor values to obtain a given gain. We wrote a wrapper function to take in the predicted and target resistances and insert them into a circuit simulation software to see the corresponding gain. This is what is displayed in the graphs on screen. Ideally, the results would follow a trend line of y equals x, as this would mean the predicted resistances produced the exact same gain as the target resistances. To better investigate error, we calculated the Euclidean norm for each set of results using the formula shown below, where E sub I is the difference between corresponding gains and n is the number of data points. A problem that we faced was the one-too-many problem, as mathematically, it's not possible to obtain 6 unknowns just from one value. If you want 6 unknowns, you would need at least 6 kind of equations to base this off of. Eunsan will discuss our solution to this issue on the following slide.
So far, each of our machine learning algorithm requires 8 inputs to operate. It needs 4 voltage values and 4 current values. User will need to calculate these 8 different values to use one of our algorithms. That is very time consuming and cumbersome. Hopefully in the future, we can modify the algorithm to take in the voltage gain as the only input and makes an educated guess about the 3 other voltage values and the 4 current values based on the training data. Furthermore, it will be neat to implement a GUI to the algorithm so that it's easier for user to use. Given our results, out of the 3 machine learning algorithms, neural network, polynomial regression, linear regression predicts the parameters most accurately. The phrase "simple is best" really hits us with this result. Our time with Opportunities Research Scholar has been very valuable. We learned the basics of 3 different machine learning algorithms, learned how to write related documents, how to present the information in a professional way. Most importantly, we learned how to approach the problem that was very open-ended. Thank you for your time.